Today, I would briefly go over some of our recent works on knowledge distillation. I call the topic of my presentation Improve Knowledge Distillation because I'm going to present a couple of techniques, especially, let's say, some improvements on original knowledge distillation that we have worked on in the past year. Let's go directly to the outline of the presentation. I'm going to introduce knowledge distillation, and also I'll mention how does KD is going to help, let's say, training or training deep neural networks. And we are going to show improvements on top of original knowledge distillation in terms of training, in terms of data efficiency, and also structure efficiency. And then I'll go over some open problems in knowledge distillation. So why do we need knowledge distillation? Just to give a bit of motivation about this talk. So originally, knowledge distillation was proposed for model compression, and with ever-growing size of the neural network, let's say parameter sizes or the number of parameters of neural networks. So the need for neural model compression would be even more vital or important. So especially for NLP, I'll get back to this, but so you see these days, like we have super large models.
Yeah, I don't know if this is my problem or it's disconnected. Right? It appears that Mehdi is disconnected, huh?
Yeah, actually, Mehdi is disconnected.
Yeah. The other benefit of knowledge distillation is on improving the performance of the model. So as I said, like KD or knowledge distillation was originally proposed for model compression, but in around 2015, and also before that, I'll mention in the next slide, but around 2018, we had another sort of track for application of knowledge distillation in terms of improving the performance of the models. And this setup is called, like originally born again neural networks. Now we call it also self-distillation, in which like you can improve the performance of a single model by distilling the knowledge from itself, from the previous, let's say, train checkpoints. So I would basically, because of these two reasons, actually knowledge distillation is very popular these days. And you might see, like you might have seen in recent publications, in many of, let's say, training related papers, you see KD as one part of the training module, and it has become very popular. So here I'm going to first introduce what knowledge distillation is, in case that you're not familiar with the technique. So KD originally was proposed in 2006 by Basira.
So Mehdi, you got disconnected during your talk, and we lost your video now. Can you just close and get back? With your video, at least we check if your video is back.
Yeah, sure. So just let me connect again my video. Sorry about that. So I have to stop share to be able to. I think my video is on now. I don't know if others have.
Can you
problems.
make it off and then bring it back?
Okay, sure.
Maybe that can solve the problem.
Yeah. Is it good now?
I don't see it. I don't know if the others see it, but I don't. Maybe we continue. Doesn't matter.
Okay. If others also, like one person can give me a feedback on this. So do you see my video or not?
No.
So maybe it makes sense that you disconnect and come back just to make sure that everything is restarted.
I think like maybe it's okay. I don't want to distract others, but
okay, so please go ahead then with your presentation.
Yeah, but I do apologize for this. I have my camera on. I don't know what's wrong with the So let's just put it full screen. And like bring my laser pointer. Yeah. So for model compression, for knowledge distillation, it was originally proposed by Basilia et al. In 2006. And at that time,
we don't see your screen now. So even sharing the screen doesn't work now. So.
Okay, so then it should be my laptop problem. So I have to maybe restart my computer.
Maybe,
or let me just try. Yeah, let me just try one, or yeah, I can reconnect with Zoom. Like, let me just,
yeah, that perhaps solves the problem. Let's see.
Yeah.
Yeah, I'm sorry, everybody, for the inconvenience it might happen during like online meetings.
I hope it's good now. I don't know.
Yes, you're back. Good? Your video is back. So hopefully your slides also will be back.
Yeah, let's see. So I just share my screen. And yeah.
Yes, we see your screen.
Okay, good. Then sorry about this issue. I just need my laser pointer as well. And then I continue. Yeah, so the first form of knowledge distillation was solving regression tasks. And it was supposed to like go from ensemble of models to a single model. So the format of compression was this way, that we let's say integrate ensemble of models into one, the knowledge of ensemble of models into one model. But later on, this knowledge distillation approach became more prominent after the paper by Hinton et al. Like in 2015. And they basically introduced this knowledge distillation for classification problems. And what knowledge distillation is, like, let's briefly just go over that. So for regular training of, let's say, classification task, you have a cross entropy loss, and you try to, like, you define a loss function between the original labels or the ground truth labels of your data and the prediction of the model. So you define a cross entropy loss between these two, and that's your basically loss function for training your model. For knowledge distillation, we have an auxiliary loss, the KD loss, and this would try to like match also the output of the student, let's say, prediction with the output of an already pre-trained model. So here, instead of having only the data set and training on top, let's say based on the training data, we also rely on a pre-trained model, and this pre-trained model, we call it teacher. And this teacher is usually like larger than the student in terms of capacity, and it's, let's say, it's able to learn the underlying function with a good approximation. So considering the let's say the knowledge learned by this teacher, we want to get help from the prediction of this network to improve the training of our student network. And that being said, aside from the regular cross-entropy loss that we had even before, without knowledge distillation, we would have another term, let's say, loss term, which is called KD loss. And this KD loss would try to match the predictions of the student with the prediction of the teacher. So we would have a KL loss between the probabilities of or probability predictions of the student and the teacher. So we hope this process would improve our training in terms of generalizability of the student model after training. And the other thing is that the teacher I mentioned already is trained on the same training data. We should be aware of a few terminologies here. We have one term, temperature, in the KD loss, that this temperature would control the smoothness of your prediction for the student network and the teacher network. We have also the term soft target. So prediction of the teacher is called soft target. And we have also the term, why do we call it soft target? So soft target is, let's say, opposite to the ground truth label, which is one hot vector. So we call it soft target because it's not only 0 and 1, and we can have a probability over all different classes. For dark knowledge, this term actually was coined by Hinton, and it points to class similarity, or somehow the knowledge that the network or the teacher network is learned after seeing all the training examples. And I'll try to explain it maybe a bit better with this example. Let's say you have a teacher network, and this teacher network is already trained on a sort of object detection task or something like that. And we show a car image to this teacher, and the output of this network, let's say for now we have only 3 classes, so car, fruit, and truck. And in contrast to, let's say, the ground truth data, which only tell you your input belongs to what class, so it's actually 0, 1. The output of the trained teacher would be somehow smooth over different classes, and we would have a particular probability or higher probability for the correct class, the car would get higher probability value but for other classes the probability would not be 0 necessarily. For here that we have a car image, for the car class we have a probability of 0.7. For fruits it's almost 0.08, it's let's say 0.1, and for truck it's 0.2. So it's somehow showing that this car image is close to or it's closer to truck than, let's say, fruit. So it gives you some extra knowledge which is called dark knowledge. So this dark knowledge doesn't exist in the original training data, and this is a sort of auxiliary knowledge that was introduced or somehow explain the success of KD by somehow can explain the reason behind why KD works. So adding some extra knowledge like in the training process from the teacher network, which is already pre-trained. So now we come back to the question of like how does KD help training? And I would say for around 5 years, maybe like the main answer to this question was dark knowledge. So this dark knowledge is somehow auxiliary information that would improve the performance of your training. But recently, let's say we had also other efforts in explaining like why knowledge distillation can improve the performance of like, let's say, models. And one of the, I would say, astonishing works is like this revisiting knowledge distillation via label smoothing regularization. And they showed a few observations that are somehow counterintuitive, and they can lead to like other explanations, and also it can cast doubt on dark knowledge to be the only reason for success of KD. So what they observed was like they did experiment on applying knowledge distillation, like trying to distill the instead of like distilling the knowledge of teacher to a student, they did the reverse process, and they did let's say they distilled the knowledge of student to the teacher. So they reversed the process, and still they saw let's say some improvement on the performance of teacher after doing this, which is really surprising. The other thing is the common belief is like you should have a good, very good trained teacher to be able to have a good distillation process, or to be able to improve the performance of the student the most. But they showed that even a poorly trained teacher can lead to like some improvement for training the student as well. So these two observations somehow led to this question that whether this dark knowledge would be the only reason that KD works, or there should be some other underlying factors. So they showed some similarities in this paper between, let's say, knowledge distillation and label smoothing. So if we consider label smoothing as a famous regularization technique, and maybe you have used it like for your projects a lot, or like at least a couple of times so far, we can find, we can see this correspondence here clearly. Like, let's say for regular training with cross entropy, we have the model prediction. Let's say PK is the model prediction, and K relates to the, let's say, the label of the correct class. And for target, we have a one hot vector of QK. That's like for kth class, this target is 1, and for others, actually it's 0. And then we have the cross entropy loss. For label smoothing, actually, everything is the same except one part. For target, instead of having the one hot target, we have a convex combination or linear combination of one hot label and one, let's say, random vector, or usually it's uniform distribution. So instead of having the one hot vector, we have we replace the one hot target with this like convex combination. And the thing is, this paper shows that if we, let's say, expand this term and put it in the cross entropy like loss term and expand it, we would end up with alpha cross entropy plus 1 minus alpha KL between this uniform distribution and the prediction of the network. So this reminds us of like the KD loss, if you remember. So like here we had the same thing, convex combination of cross entropy plus the KD loss. So the KD loss was also a KL between the teacher prediction and the student prediction. So for label smoothing, we end up with the cross entropy as like we had in the cross entropy term, like similar to KD, and the KL term again similar to knowledge distillation. The only difference is instead of the teacher prediction, here we have the uniform distribution. So then you can find the correspondence between the two. Apparently, with this explanation, we can say knowledge distillation is a particular form of label smoothing. And it would be, let's say, if we replace this uniform distribution with the prediction of the teacher, it would be exactly the same. So we can say knowledge distillation is a trained sort of label smoothing. And then it gives us one more explanation on why knowledge distillation can help training of neural networks. And then this would be because of regularization effect. So because of this regularization effect, then we would be able to answer some of the, let's say, unintuitive, I would say, observations that we had or we saw in this paper. Like if KD is a regularizer, then we can expect that even a student can have some regularization effect in training the teacher. So we can explain why reverse KD can work. Or even a poorly trained teacher still can be a good regularizer for the student. So it won't be worse than uniform distribution that we have in label smoothing. And the same thing for student prediction. So student prediction won't be worse than like a uniform distribution that we have in label smoothing. So if label smoothing can play some sort of regularization effect on training, so then this KD and these even poorly trained networks, or let's say small capacity networks, can also improve the performance of training. The other thing is, now we come to self-distillation. So for self-distillation would be the same thing. So maybe even you don't need the teacher, the network can regularize itself. The prediction of the network during training can regularize its training for, let's say, for the next or for the rest of the training. So then we have another answer for how this KD is helping. And then we have also like another hypothesis about, aside from regularization, aside from dark knowledge, we might have some inductive bias transfer, and KD might help in transferring inductive bias from one network to another network. So what does it mean? Like, what do we mean by inductive bias? So if we put data aside, any other sort of bias that we have in our learning algorithm, it would be called like inductive bias, like the choice of the architecture, the choice of your training optimizer, let's say, the choice of the loss function. These would fall into the, let's say, we can, let's say, call these like inductive bias that would impact your training later on. So then we have a few papers, very recent papers, that they show the importance of knowledge distillation in transferring this inductive bias. And I want to highlight one of them, the second paper here, that they show that, for example, if we do knowledge distillation, or if we distill the knowledge of a CNN network to like a multi-layer perceptron for MNIST, like for let's say the MNIST task, like or corrupted MNIST task, then the training path of the MLP would become very close to the training path of the CNN, which is very again surprising observation. So if I want to explain a bit more about this, so let's say you're if you want to choose one architecture for like training an image classification task, I think your natural choice would be CNN. And you would not go with multi-layer perceptron because CNN has some spatial invariance like features that can fit well to the image, let's say, type data compared to MLP or like other, let's say, RNN. So then if you train like, let's say, one CNN network on MNIST and one MLP network on MNIST, so you can see the training path of these two networks would be completely different. And the interesting thing is, like, you take the last checkpoint of the CNN and you distill the knowledge of this CNN to like a sort of MLP, the same MLP, like multi-layer perceptron neural net, which is trained from scratch. And then after this distillation, the training path of this NLP network would become very similar to CNN, which is very interesting. And then we have this hypothesis that maybe KD can also help transferring the inductive bias. So the details of these I leave to you to like go to those papers and maybe read them. So now we have these three main reasons that like, or at least hypothesis of how like does KD help. And now I come to applications of knowledge distillation, especially for NLP domain. I would say we had a breakthrough after emergence of like these pre-trained language models in NLP, especially in the NLP domain. And one other phenomena here is that, like, in order to improve the performance of these models, people or companies are trying to increase the size of these models and like make them more and more over parameterized. So considering that, then if you want to deploy these models, you need to compress, like let's say for on-device applications, or like to improving their speed for inference, for giving it to end user for their own training, these things. So you have to compress these super large models. And one natural choice can be, okay, vanilla knowledge distillation can help here. But unfortunately, it's shown in the literature that vanilla knowledge distillation is not perform, let's say, that good on this task. And this apparently, like, there should be some other underlying factors that make training of like these like let's say or applying knowledge distillation on these over parameterized networks like more difficult. So we have several evidences on that, and then we come to the question of like how we can improve knowledge distillation, especially for these oversized networks. We have a few works in the literature. I'll go over some of them in my next slides. And especially I come to I would say the main motivation of this presentation, which is how we can improve knowledge distillation, especially for NLP applications, but most of techniques we are, like I'm presenting in this presentation, would be like you can apply it on other, let's say, training tasks as well, like computer vision or speech like domain. So we want to show how we can improve knowledge distillation, and to answer this we go to three different directions or perspectives. Like one is about data efficiency, the other is about structure efficiency and training efficiency. And I divided into these three pieces because if you see like the training pipeline of knowledge distillation is composed of these three components. So like we have data, we have the model and the structure of the model, and also the training and the loss functions and training objectives. So I'll start from the training part, and then I'll go to data and then the structure. So for training, basically, one particular problem that I mentioned in my, let's say, 2 slides ago, was about capacity gap problem. And what do I mean by capacity gap, and why why is it important? By capacity, it's shown that knowledge distillation is not that successful to transfer the knowledge of very large teachers to very small students. So when the gap between the, let's say, when the capacity of the teacher is much more than like the student, or when the gap between the capacity of the teacher and a student is too large, then KD would have difficulty in transferring the knowledge properly and getting, let's say, a successful training. So this was initially shown in a paper from like DeepMind in AAAI 2020. And
may I ask, what you see like too small or too big? I mean, what's the difference? Do you talk about like number of parameters that they are too big?
Yeah, exactly.
Number of layers to be too different?
Yeah. So I'm saying about the number of parameters, especially.
So what is that order? How much is compressed more? You think that the KD is not that much?
Yeah. So it's different for computer vision and for NLP. But let's say, especially in this paper, we are talking about, for example, a 24-layer teacher and 4-layer student. Like,
the order is like 5 times.
Yeah. At least for the bear type models, yes.
What about the computer vision? Because, well, the pixels include more information. I don't know. It doesn't mean that we can.
Yeah, exactly. So for that we have like ResNet like 100. Let me just to be so we have ResNet 110, and then we go to 8-layer version, ResNet 8. So and also so this is the order that we, at least this was introduced in the original paper of teacher assistant that I mentioned here. So this problem would be, I think, more important in NLP because the size of the teacher in NLP is even larger than computer vision. The solution in the TAKD paper, teacher assistant KD paper, was somehow filling this gap by introducing a sort of intermediate network. And this intermediate network is called teacher assistant. So this teacher assistant is going to, let's say, learn the knowledge from the teacher at the first place, and then instead of dealing with the teacher, we would distill the knowledge from teacher assistant to the student. So a student would not deal with a super large model, it would deal with a smaller, let's say, or intermediate size network. So that's the idea here. And also they say, if this gap is like very large, or if you want to improve this, let's say, distillation process, you can rely on multiple teacher assistants. So let's say you want to go from a teacher with 10 layers to a student with 2 layers. So we can add multiple teacher assistants, one with 8 layers, one with 6 layers, one with 4 layers. This solution, actually, from beginning, we didn't like it much, especially for NLP, because training these intermediate teacher assistants are also very expensive. And this solution would not be scalable that much. Aside from this, like, we would have error propagation. Let's say the training process for teacher assistant would not be like error-free, and we are somehow I would say propagating these errors to the student model at the end. So we also extended this work to like NLP domain. It was only like on CV, computer vision. So we said we have to come up with another solution which does not need a teacher assistant, but maybe in terms of rationale that they use for adding a teacher assistant, we try to inspire by that. And we would say for student network, it might be, our hypothesis is that like a student network is a low capacity model and it wants to follow a very complex, let's say, teacher network. And this teacher assistant maybe makes the process of training more gradual or smoother. Instead of dealing with a complex, let's say, network, or let's say a sharp loss function, when we have an intermediate layer, maybe like this, the output of this not intermediate layer, the intermediate teacher assistant, then the output of this model would be more smooth, and the training process would become more gradual. So if we consider this, then we thought maybe we can play with the output of the teacher, and we remove the teacher assistant completely, and we directly process the output of the teacher, and we keep the training still smooth, but instead of adding a teacher network, we play with the temperature parameter that we have in knowledge distillation. And instead of having a static or fixed temperature, we go with a dynamic temperature. And this temperature is going to play with the smoothness of the output of this network. So for teacher, we add a sort of annealing function. So this annealing function would determine the temperature value over training. And this annealing function is applied on the output of the teacher. So at the initial phase, so this figure would be more clarifying. So let's say we have a pre-trained teacher with complex output, or like, sharp output. In order to make the training process smooth for the student, we apply this annealing function. At the beginning, the temperature is set to maximum, and then it would smooth out the output of the teacher almost it would be or it would be more flat, and the student would be able to follow it much easier. And gradually during training, we increase this, we decrease this temperature. And at the end, we would set it to 1 that the student would follow the same or the original output of the teacher. So that's what we propose in stage 1 of this training. And in stage 2, actually, we just apply cross-entropy loss for training the students. So if we want to see one example here, we generate one synthetic data set, and we train a one-layer network with 100 neurons on this, and you can see the output of this teacher network is annealed with different temperature factors. And also in terms of so for at each let's say training time, we start with highest temperature and more flat output from the teacher, and gradually decrease the temperature. And you can compare the performance of regular KD with annealing KD. Especially regular KD is not able to capture this part of the let's say the model, but our annealing is able to completely fit to the curvature of your function. So that's one simple example to explain how this annealing works. And then for experiments, as I mentioned, we tried it on both computer vision or image classification and also natural language understanding. For image classification, we followed the same setting as the TAKD paper. So we had our results on CIFAR 10 and CIFAR 100. I think you know these data sets better than me. And in terms of the networks, we had the ResNet 110 and CNN 10, and the student network of ResNet 8 and CNN 2. One thing that I want to highlight here is we consistently beat TAKD for all scenarios I mentioned for the CV experiments or image classification experiments with roughly a good margin. The other thing is I go to the glue task, generalized language understanding evaluation benchmark, which is consists of several classification tasks, mostly binary or ternary classification on, let's say, language inference tasks paraphrasing and sentiment analysis, different sort of tasks that you can maybe check this. I don't, for the sake of time, I don't go to the details of these 9 different language understanding tasks that this glue benchmark has. So for the glue benchmark, we started with Roberta Large teacher, and we trained the teacher assistant Roberta base with 12 layers, and our student has 6 layers. And for this experiment, actually, we on average, especially I would say for 8 out of 9, or so for 8 out of 9 we can beat TAKD, and on average we are much better than TAKD and vanilla KD, and also training from scratch. The other thing is like these were like the dev results, and also for test we compared on GLUE leaderboard, and this Annealing KD on GLUE leaderboard is also consistently better than TAKD and Vanilla KD with a good margin. This 0.5% in GLUE average score is actually something I would say noticeable, that you can even publish on this when you improve like this much. And like we had this paper accepted in EACL. The other setup that we tried was even increasing the gap more, and we changed our student from 6-layer Distill Roberta to Bertha Small with 4 layers, and we observed that when the gap becomes even larger, the improvement of our model become like more significant compared to TAKD and Vanilla KD. That's another I would say good point about this model. So
Mehdi, yeah. Can you tell us what's the reason? The annealing is the reason, so you have a temperature, that's why it's happening?
I think this, yeah, so we have some theoretical justification for this as well. Let's say, especially, I would say what we saw in terms of, sorry, yeah, I just hide that slide. I didn't remove it, right? I hide it. Okay. I don't have it in this presentation maybe, but I had the theoretical also insight about why it works. And one reason for us is like, especially we saw this, we tried to plot the loss landscape, especially for the ResNet experiments. And we show that, so for when we have a let's say sharp loss landscape, the training generally is harder. Training a neural network would be even more difficult. But here, by applying this annealing factor, we reduce this like the sharpness of our loss landscape, and we make this training process more gradual. So that's one reason behind it. I would say from also we had one other explanation for this based on VC dimension theory, so in the paper, but for the sake of time I didn't like put it here. But I think the gradual process is the main I would say reason.
Okay, thank you, Mehdi. So please.
You're welcome. Yeah. So then I continue with just summarizing this annealing part and the differences that we have. So the first difference is like our annealing process is 2-stage instead of the 1-stage Vanilla KD. So we have the KD loss. We apply the KD loss first, and then we go to the cross entropy loss. That's number one. Number two is about the loss function that we have. So we don't have KL loss, we have a mean square error loss instead. And we don't apply temperature to both student and teacher. We have just the annealing factor or function applied to the teacher. So the student would just try to follow this annealed version. And the third part is the temperature, which is fixed in Vanilla KD. And here we have a dynamic temperature assignment. Then I go to the second part, which is data augmentation in my presentation. So for data augmentation, you know, like data augmentation is a popular technique for improving generalization of your model. Especially, and we have different types of like data augmentation techniques, like heuristic-based, model-based. For heuristic-based approaches, like in computer vision, We have image rotation, translation, like playing with RGB intensities, like interpolating images. Like these are very like heuristic approaches that people use for augmenting data in computer vision. We have similar techniques in NLP, like by replacing words with their synonyms, like paraphrasing, these sort of techniques for augmentation. One major difference between NLP and computer vision, let's say for heuristic-based approaches, is that like for images, when you do augmentation, like these heuristic approaches, with these heuristic approaches, actually you will still see the same image. Your perception about the object or the image is not going to change. But unfortunately for NLP, it's not the case. Like for text, let's say, even if you replace some words with their synonym, there is a chance that you change the whole meaning of the sentence. Like, or even you change a meaningful sentence to a nonsense sentence. This sort of discreteness we don't have in computer vision, and makes the data augmentation process in NLP a bit more difficult. In terms of model-based techniques, we have like two classes actually there. Like some models, they need task-specific, let's say, training, and some they do not need. Like, for example, adversarial data augmentation usually is task-aware. We have other techniques like back translation or using contextual data augmentations like BERT that they don't, let's say, they are independent of the final task that you want to like apply data augmentation to. So what's the relation with knowledge distillation? So for knowledge distillation, there are a few problems. One is the data augmentation techniques are usually like designed for a single network, like if they are model aware at all. Like they are not tailored for knowledge distillation, which has actually teacher and student. With that being said, actually, I want to introduce the second problem, which is the data gap problem. So for the data gap problem, we know like our training data is limited. So we're not our training data is not going to cover the entire input space. So we have some gap in the input space if we consider the training data. The thing is, your teacher assist, your knowledge distillation loss would guarantee that, like, for over your training data, like a student network would follow the teacher network, or it would get close to the teacher network. But what about like in other regions in the input space that we don't have any training data for? So we call it like the data gap problem. And we say like with a high chance, actually the two networks would diverge from each other for or they can diverge from each other like for other regions in this input space. The other thing is, like, most of the data augmentation techniques are not sample efficient. So usually people, even if you want to augment data to your like training data, like you just add 5, 6, 10 sample to your, like for each training data sample, you like augment it with between 1 to 10 sample, but without any, let's say, specific rationale about like how many samples we should use there and being sample efficient. And the other thing is, like, most of, not most of, like I would say, usually like these augmentation techniques in NLP, they don't keep the semantics of the training sample. Like after augmentation, the augmented sample would not be necessarily semantically meaningful. So we had a solution for especially this data gap problem. And also our solution was tailored for knowledge distillation. Considering that, considering this data gap problem, for example, here I show the student network. This is just a synthetic example just to clarify the problem better. We have 3 training sample, and like around those training samples, like the student and teacher network, the black solid, let's say, curve and the blue solid curve, actually they cross each other, but in between there is no guarantee that these two would follow or would match. Actually, the same thing, like in this example, we have the same, we are explaining the same thing. And then what can be the solution? So we proposed a minimax approach for this problem. And this
Mehdi, I just want to mention that the time is getting over. So I wondered how many slides do you have?
I have more, but I'll stop like in a
so that we have some time to have 5 minutes for questions if there are any.
Yes, for sure. Yeah, so
Please.
I'll stop after this actually data augmentation part. I don't go to the next part about structure efficiency. So for this data augmentation, for this let's say data gap problem, we propose a minimax approach. And this minimax approach, like for this minimax approach, we have 2 phases. One is the maximization phase and the other one is minimization step. So for maximization step, we would try to generate the best, I would say, augmented data, which would lead to the maximum divergence of the 2 networks. So we would search somehow over the input space to find the regions where like the student and teacher like diverge from each other maximally. So that's about the maximization step. So how are we going to find this augmented sample? So that would be a very good question, and the answer is with a generator. So this generator network can be any pre-trained language model for our case. Maybe for image, it can be like any image generator, like, but for us, like here is like a BERT model. And for this generator, we randomly mask some inputs in the input, some tokens in the input data. And the network, this BERT model, would predict those masked tokens. And the thing is, in order to guarantee that like the output of the teacher and a student would diverge maximum, we apply a loss function here, and we optimize the parameters of the generator in a way that it will, like the output prediction of the generator for those masked tokens would lead to the maximum divergence between the teacher and the student. So that's the maximization step and how we get the augmented samples. And then we go to the minimization phase, and minimization phase would be really easy. Like we have our optimal augmented samples and we just add them or concatenate them with the original training data, and we go to the regular minimization step. One point that I want to highlight here is that whatever we do for data augmentation here would be on, like we do it on label. And we don't add any label to the augmented sample. We can do this here because we have a teacher network we don't need necessarily a label to be able to do the minimization. So somehow we guarantee that for those augmented samples, the student would be able to follow the teacher properly. Like that's what we propose. So for the experiments, actually this paper accepted in ACL, like in the main conference, and like we had very solid results or promising results on this, we call it MATE KD approach, and especially for knowledge distillation, it beats all the state of the art, and it got rank 1 on the GLUE leaderboard for 6-layer BERT models. I just want to show some of the, let's say, generated augmented samples. So let's say for original samples that we feed to our model, we mask some of the tokens in the sentences, like you see for the first one, the blue words are masked, and then we have the generated, let's say, augmented version of this with some other words replaced, like in the position of like original masked tokens. But after augmentation, the generated sample actually is meaningless, unfortunately. We don't care about the, let's say, augmented sample much to be like meaningful or not. But that's one consideration that actually these generator-based techniques, they are not able to keep the semantics of your augmented data. Yeah, so MATE KD outperforms the state of the art, but it needs generator and it's not necessarily semantically meaningful. I wanted to go over for one solution for this semantic issue, like that, how we can keep semantic and do data augmentation. This one actually also was accepted in ACL, and maybe if you're interested, you can check. The paper is on archive now. And then I don't present this. And the last part of my presentation was on a structure efficiency for knowledge distillation and how to apply distillation on intermediate layers and solve the search problem, which already I think we had one presentation on this from Payman. So my presentation on this part was quick.
We have to cut it.
Yeah. So I'm open to the questions.
So thank you very much, Mehdi.